DNA building blocks work a lot like interlocking toy bricks. Each brick is a single strand of DNA that is 42 bases long. Here, each letter represents a sequence of DNA that is 10 or 11 bases long. We can think of the DNA strand folding into a block-like structure. We'll show its actual shape in a few moments. Each block has the ability to connect to another block, but it won't connect to any block. It connects only to a block that has a sequence of DNA that complements a segment of its own DNA. In this case, a sequence represented by the letter J connects to a block with a complement of J in its strand, J'. The blocks self-assemble, connecting only in areas where the DNA sequences complement each other. The structure can consist of any number of DNA blocks. Here, we show a structure made up of 362 blocks. Each block has a unique DNA sequence, and each block has a specific location within the 362 block structure. To design a structure, all we have to do is withhold specific blocks before we allow the blocks to self-assemble. If we withhold all of the blocks in the center of the block, for example, a rectangular ring forms. Here, we've withheld blocks to form the letter A. Many different shapes can be formed, including an eagle head. Here's a more accurate representation of a strand of DNA that will form a block. This strand is called an SST, which stands for single-stranded tile. It won't form its block shape until the bases that make up the strand encounter and connect to complementary bases from other strands. The SSTs are in constant motion, always wriggling and bending. This motion is restricted as the SSTs come together. The yellow and brown SSTs begin to take on the block-like shape as they connect to other SSTs. As mentioned earlier, only those SSTs that are needed to form the desired shape are available. We've shown this structure forming on a plane, but it actually curls as it forms. It flattens out only after it settles onto a plate. Researchers at the Wyss Institute have created many shapes in the lab, including these. The approach is simple, robust, and versatile. We believe it could enable the creation of new nanoscale devices with a wide range of applications.